I think our previous class. Last week, you bear with me that we started with ionic product of water. And under ionic product of water, when we spoke about the ions that constitute water formation. We spoke about that. We were able to derive the units for the ionic product of water. We were able to find the calculation using the Kc, where we said the Kc is the equilibrium constant given a chemical reaction. We use that. We're able to equate it to the ionic product of water, which we were given to be Kw. We also were able to derive the the constants, the numerical constants of the ionic product of water. We looked at all these the other time, and from there we solved questions under it. When you are given when you are given when you are given the concentration of the aqueous solution and so on and so forth, we made some calculations and deductions last week, and I hope you all understood. I don't think some of us, I think some of us went around. We have it on YouTube, so you can just go online and go and revise. Let's, just as I said yesterday, let's all take our destiny into our own hands and be part of the class. And that is it. Be part of the class. Be part of the class, so that we wouldn't always have to be going back. So that is it. Let's try one question, then we can continue. I don't know if you did this the other time. You said calculate the hydro ions. Calculate the hydroxide ion concentration. Calculate the hydro. I'm coming, please. Calculate the so calculate the hydroxide ion concentration at 25 degrees in a solution whose pH is 5.78. Did we do this the other time? Maureen, did you do this the other time?
Sir, please, I'm checking.
Check for me. I think we solved it.
Sir, 5.78.
Oh yes, 5.78.
Sir, then you've done it.
We did it. Oh, okay. So, did you do, given a solution, a given solution has a pOH of 4.5? Did you do the other time? pH of 4.5. Calculate the pH of the solution. Did we do it?
Sir, please, no.
Okay, so let's do it. A given solution has a pOH of 4.5. A given solution has a pOH of 4.5. Has a pH of 4.5. Has a pOH of 4.5. Given solution has a pH of 4.5. Calculate the pH of the solution. It has a pOH of 4.5. The question is calculate the pH of the solution. pH of the solution. Then number 2, determine the number of hydrogen ions present in 300 cm cube of the solution. Determine the number of hydrogen ions present in 300 cm cube 300 cm cube of the solution. Given Avogadro's constant to be 6 point, given Avogadro's constant to be, Avogadro's number to be equal to 6.02, 5.23 times 10 to the power times 10 to the power, so the 23, I guess. The 23 particle per mole. So let's do it. Who is done? Who is done? Who is done? Who is done? Who is done?
So the pH 9.5.
The pH is 9.5. Yes. Mildred, talk to me.
Yes, the pH.
The pH is what?
So
9.5. Okay. Okay. So
9.5.
pH is equal to 9.5. 9.5. Good. 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 My girls are good. That means the pH is okay. Okay. So let's continue. So determine the number of hydrogen ions. So we are doing the second one. Oh. Okay.
Please, I
Yeah.
5.71 times 10 exponents 13 ions.
Okay. Okay. Who else? Who else? Who else? Let's wait for the rest too. Tina, what did you get?
Please, I'm not done. Almost.
Okay, Mildred, I'm waiting for you. For Cindy, Ruben, I'm waiting for all of you. What are we getting? What are we getting? What are you getting? So it means that the pH of the solution is, what do you call it? It's basic. Looking at this, you can say it's basic. Or
Yes, sir.
can we please continue? So let's do the number, the II, or the 2. The 2, what are you going to do? So we know that now we've been able to find out that our pH is equal to 9.5. Yours is correct, and your work is correct. So our pH, if you want to get the concentration, what do we do? What do we do? We want to find for that of the hydrogen ions in the solution, given our pH. What do we do? So the concentration H will be equal to 10 raised to the power 10 raised to the power the pH, which is 9.5 minus 9.5 minus 9.5. Sorry, 9.5. What are you getting?
30.162 times 10 exponent
3.162 times 10 to the power
minus 10.
10 to the power minus 10. So that's what we are going to get. Now, after getting this, then the question states that we should find for the number of hydrogen ions present in 300 cm cube of the solution. So once you've been able to find for the this calculation is calculating for, what do you call it, the concentration of the hydrogen ions, and this all this was derived from, pH is equal to minus log 10 9.5, and we want to get the solution. So what we do is we are going to do this mathematics. I hope you understand to this point. There's a log a log derivation, and so this becomes a concentration. So we can relate concentration in terms of, before we can able to find the number of this thing, the number of hydrogen ions, we are supposed to find for the number of moles before we can be able to find for the number of quantity or entities. And so we know that number of n is equal to C times V, right? I hope my formula is correct.
Yes, sir.
So
Yes,
number of
please.
moles should be equal to, we have our concentration to be 3.16 times 10 raised to the power minus 10
Negative 10.
minus 10. That's what we have, times our, what do you call it, our volume. But you know that the volume is in centimeter cube, so we have to convert it to dm cube. So when we are converting this to dm cube, we just simply divide by 1,000. So we are going to get 300, because they're all in cube. 300 cm cube divided by 1,000. That's what we are going to get. So the answer we are going to get, what are you going to get? Those with the calculator are going to get 9 point something something.
9.49 times
9.4
87 times
okay, 87 times what?
10 exponent negative 11.
10 exponent negative 11. So we are going to get this. Now after getting this, we've been able to find for a number of moles. Then now we can also relate it, given Avogadro's constant, we can be able to find for the number of, what do you call it, number of ions. And the number of ions will become a small n, capital N, or
Capital
N is equal to what? Capital N is equal to small n times L, right?
Yes, sir.
Yes, sir.
Well, we know that our n is equal to 9487 9487 times 10 to the power times 10 to the power minus 11 times our Avogadro's constant, which is given as 6.6.02 times 10 raised to the power
23.
23. So the answer we are going to get will be a number of hydrogen ions. What are you getting? 5.7 5.714.
7.711.
That's 1
1.
Okay.
Yeah.
Times 10 raised to the power 13,
13.
ions.
Yes.
Ions or entities. Don't worry. So there's a calculation or a typical solution. And the other time last week I gave you all the formulas that you need to solve questions like this. When you know this, finding the quantity of this and these, they are all basic formulas we know from what you call mole concept. So we just have to incorporate that into the ionic product equations or formulas, because you know that there's one formula which is pH plus POH is equal to 14, that we already know, and that is where we derive our 9.5 from. And we also have the main constant of the distance, the constant of the kW you were given to be 1.10 raised to the power 1 times 10 raised to the power minus 14. I guess we studied that at a constant temperature. We studied that, and so we have our formulas and how to find for the Kc. That is the product of the what do you call it? The product of the product all over that of the reactant. We studied all this thing the other time. Today we are going to talk about basically two main things. We are going to talk about Ka and pKa. Now when we talk of Ka, then we are talking about the acid dissociation constant. You know, K is always a constant, so we are talking about acid dissociation constant. Then the pKa is the pH of the, what do you call it, the acid dissociation constant. So basically that's what it means. And so today we are going to talk about Ka and pKa. Let me pick this thing. No. So today we are going to talk about Ka. And when the thing ends, you start again and you end. And pKa. And from there we will do pKb2, pKa. Now when we talk of Ka, we said that is the acid dissociation constant or acid ionization constant. And other when we were doing the ionic products of water, we were able to break down the products of water and so on and so forth to be able to get both the reactants forming into a product, and from there we were able to get the Kc, which is the equilibrium constant of the water formation, where we had a certain H something all over H2O. I explained that the other time using the equilibrium constant. We had a certain H plus coming into contact or multiplying a certain OH minus all over H2O. I hope you remembered. We did that the other time. Now in today's class, it's basically the same thing we are going to do. But when we talk of, we are going to consider weak acid. You know, weak acid dissociates only partially in the solution. But we know strong acids dissociate wholly or completely in the distance and water. So here we are going to consider weak acid. That is where we can be able to locate some ions and so on and so forth. So weak acid dissociates only partially in solution. Now, representing weak acid, we can represent weak acid as Ha. And so let's represent weak acid as Ha. And so our weak acid, we can represent it as H capital A. Now, when our weak acid comes into contact, which is our Ha, comes into contact with water, which is H2O, which is our H2O, sorry, H2O. What we are going to get, this is the sign. This sign is supposed to be, what do you call it? The equilibrium sign, reversible sign. So it's equal to, you are going to get, you bear with me that this H will come and add this one. Now when this H comes to add, this hydrogen, don't forget. Because the whole of this is an acid, but this shows that this shows that it's an acid. So this is a hydrogen compound. So the hydrogen compound will come and add to this, giving us H3 plus. H3O plus. H3O plus. Now plus HO plus the A will become minus, A minus. So this will be A minus, raise the power minus, and this one will be A subscript 3O, raise the power plus. This is already this. Now, if you have to find for the dissociation constant of this, then you bear with me that it's going to follow the same principle. Ka is equal to, using the equilibrium constant, is equal to, or should be equal to the product of the products of the chemical reaction. So that will have to do is, so the product of what we call it, the concentrations of the chemical reaction. So we are going to get H3O A3O into bracket A. This A minus, all divided by, we are going to get the first, what do you call it? The first HA plus H2. So that will be the product of the two. So it will be the product of the two. Product of the two. HA H2O. Sometimes the water components can be negligible, so sometimes we don't even add it. Sometimes we just do it all over HA, because we believe that after this thing we are going to get it's going to be added to this and so on. But for this thing's sake, we can leave it like this. Sometimes we may choose to even ignore the H2O component in it. Sometimes they are negligible. The question will tell you that it is negligible, so you just have to neglect it. And so based on what the question says, so that is it. Now let's take note that the Ka here is the acid dissociation constant. So the rate at which the acid dissociates in water. And so that is Ka here. Now, or in other words, we can say acid ionization constant. That means the rate at which the acid ionizes in water. That is it. And here we are talking about weak acid. We know that weak acid ionize partially in water. Now, we are saying that the ionization constant is unaffected by concentration. It is not affected by concentration. However, it is influenced by temperature change. You realize that when we talk of concentration, then we are talking about a certain quantity of maybe a solute in a certain solution. Now, if, for instance, if you want to talk about the rate at which something will dissolve in water, the concentration does not affect it, in the sense that if it will dissolve, it will dissolve. If you add more solute in the same water, it won't do anything to it. But then temperature can allow it to temperature can have an effect on it. That means causing it to dissolve much better. I don't know if you get my point. So for instance, if you even pour water in water, oil in water, and you want the oil to dissolve, you know that oil and water, they are not mixable. So no matter how much you pour water in it, it won't have any effect. But however, if you want to add maybe heat, there are some instances you might see a little bit this thing. So sometimes occurs. For instance, if you put salt in water, you already know that salt will always melt in water. It will dissociate or ionize completely in water. And so the more salt you add, that's not really affected, because the more salt you put, it will dissolve. But temperature can have an effect on it, in the sense that temperature can increase or can speed up the reaction. I hope you are getting it. So we are saying that the Ka is unaffected by concentration changes, but it is influenced by the temperature changes. So Ka shows that extent to which an acid is dissociated. So we are talking about the Ka is and that is the measure of the strength of the acid. And so the Ka is the measure of the strength of the acid. You bear with me that if the acid dissociates completely in water, then it means that the acid is a strong acid. Now, when it dissociates, or when it dissolves partially or partly or halfway in a solution, then it means that it's a weak acid. Now, the higher the Ka value, the smaller the pKa. And so I'm going to explain it to you. And so the higher the Ka, that means the higher the Ka value, the smaller the pK. When I say the pK, I'm talking about the pH of the solution. And so that is to say, we know that the pK will still use the same formula. pK was equal to the minus log. You know, we are talking about log here, minus log of Ka. That's what it means, minus log of Ka. So that is the pKa. Now, so the log, let's not forget that the log is to base 10. So the base 10. Now, an acid with a higher value of Ka is stronger acid. So any acid that has a higher value of dissociation means that the acid is a strong acid, and as a result, we'll have a smaller pKa, because you bear with me, when we're talking about the pH scale, the smaller values constitute that the acid is a strong acid, and the larger values, the larger values constituted that the acid is a weak acid. And so that's what it means. And so an acid with a higher value of Ka is a stronger acid than the acid with a low value of Ka. So that means if you have a lower value of Ka, then that means it's a weak acid. That's what I mean. An acid with a higher value of Ka shows greater dissociation than the acid with a lower value of Ka, that I've already said. So for instance, if you have an ethanoic acid and you have maybe HCl, and given the values, you should be able to tell that, okay, this one will have this one will be a strong acid or a weak acid based on the Kas you are given. That means the one with the higher Ka, that means it's a strong acid. That means it dissociates completely or almost completely in water or in any aqueous solution than the one with the weak distance. This thing will go off right now, and we'll start again. So that is it. We are going to do some calculations and how it is calculated and so on and so forth. Then when we finish, we'll talk about the KB and the PKB. That has to do with the base and the PKB. That is that of the base too. So that is it. We're waiting for the lesson to end. So so these are one of the formulas we are going to use together with all these things, and that's what we are going to use in our calculations. We're going to use in all our calculations.